Yeah. So in this short video, we would look at the frequency response, right? Um, in the sense, we are going to talk about this one of the figure of merit in the vertical, which was called speed, right? If you remember, talked about the speed um, in that octagon which we had. So there was gain and there was speed, which is also um known as, you can define this figure of merit in terms of bandwidth. More the bandwidth, more there is possibility of having speed for the same gain, right? Um, so let's first understand what is the speed, right, and why in these circuits, which are typically, now we are looking at the MOSFET-based circuits. So where is this speed limitation coming from? So you saw that uh, we had this MOSFET, which we described for our amplifier action. So because we are only working in analog domain, when we look at this amplifier, we can define this as a small signal. So this has been what we have uh, come down to this model to easily calculate the gain. And if we look at this, when we describe the gain, so for particularly, let's say for common source, so common source means that your source is grounded, right? Um, it's a ground, and yeah, so your G is Vi, and your D is V, right? And in that case, if we define our V out by V in, we saw that we get something called GM, right? And you see that from this gain, if one is looking at, do you see any speed limitation? Because it appears in this particular, with this gain, that as soon as I apply any input to my, so let's say if I have a microphone and as soon as I apply any input to my analog circuit, instantly I'm going to get this up, right? Because there is no notion of that you would have any kind of speed limitation from this kind of gain, right? So now if you were to see electronic circuits and you were to think about uh, what what kind of basic elements, electronic elements, give you this speed limitation or the notion of speed. So where is it coming from? Because in resistor, you see that it's just dissipating energy, right? So that means I'm passing a current and it's just dissipating energy. But where is this notion of speed coming into our circuits? And probably you have done a lot of this in your basic electronics and earlier courses. So this basic speed limitation actually in our circuit comes from the storage elements, right? Which are which take some time to store the energy. They are not dissipating. They're taking some time to store the energy or release the energy. And that is what gives you this speed limitation in your circuits, right? So now one of the storage element which is very quite evident in our circuits, right? In most of the analog circuits is capacitances, right? And one of the small example we can see of this speed limitation, we can see if we had a resistor, right? And if you have a capacitor, let's say, this is a very standard RC circuit which we know of. We apply an input. Do we have the output instantly available? No. And that is what we could see from even the time domain equation. We could see that it takes certain time, and I think this was given in your one of the earlier quiz we have. We saw that there is a time which you have to spend. So to, let's say this was initially 0, right? So RC, which is spent from your output to go to 63% of your input, right? So that is the speed limitation clearly, because we see that in time domain, how do we see that there is a time you are taking to basically charge the element. And if we were to do this in terms of our frequency response, because we know that this element can, so can be termed as 1 upon sc or j omega c, right? Uh, so in Laplace or your frequency domain, we can see, and then when you uh, what do? You do the transfer function, you will see V out, and now we write in terms of S. So right, V I, what it would be? It would be 1 upon SC, right? And from that, one can write this in this form. Let's say, or yeah, so let's write in terms of S itself. This is omega naught, and omega naught is 1 by S. You see a relation between these time constants and the frequency which we are getting, right? It would become more evident. Let me just divide this here. Yeah. So if I were to plot this, so there is a way that I can visualize this, right? Frequency response, like how we do the time response, we plot time with the whatever voltages or currents we have with time. Similarly, here we plot this gain which we are getting, which is obviously frequency dependent with frequency, right? So that is what we know as the Bode plots, which you would have seen, also known as Bode plots. Yeah. So this is the frequency response which we are plotting with omega, and you see that what is that you see here? That when there is omega is very small. So this is if I write this in terms of omega, this would be 1 upon j omega by omega naught, right? So we see that when omega naught is omega is very small, then you see that the gain with this term basically disappears. The gain is 1, right? And this is the mod we write, because we are interested in the mods, and mod of AVS would be, this is a complex number, so this would just omega by omega naught square and root of that, right? Because this is a complex number, so it's a square plus b square root of that. So that is your gain. And now from this gain, if one needs to plot it, let me go to the next page and plot it. So let's say from this RC circuit, we got AS, mod of AS actually, which is 1 upon omega by omega naught square, right? And we are trying to plot this gain with frequency so that we can look at the frequency response, right? That how does this gain changes, and we see at omega equal to 0 or very small, which means we divide it in 3 regions, right? We can say when omega is much smaller than omega naught, this is the region where omega is nearly omega naught or in some range. And this is the region where omega is much greater than omega naught. So when it is much smaller, that means the gain is 1. And when omega turns omega naught, we see what happens. The gain basically become 1 by root 2, right? So 1 by root 2 means that, so this gain at omega equal to omega naught becomes 1 by root 2. And if one needs to describe this in terms of log, right? Which is what we do. This is typically described in dB, and this is volt per volt, right? Which we know. So how do we describe it in dB? In dB, this term is simply 20 log 10 AVS, right? That is in dB. So then it would be 20 and minus sign obviously, and this would be root, so that would be 2 again, log 10, and I think root 2 is 1 by half, so that would be 1 by half and 2, right? Log 2 is I think 0.3 if I'm correct, so 0.3 into 10, this would be minus 3, right? And 1 is, so for omega less than much more omega naught, we saw AV was 1, which in dB, how much would it be? 20 log 1, right? Which would be 0 dB. So this was 0. And what happened at omega naught, that I saw a decrement in the gain by a factor of minus 3, right? Because 0 and then gain at omega naught was minus 3 dB. So there is a decrement in the gain for minus 3, and then it goes with the, it keeps decreasing with the, and how does it decrease now? So if I take, let's take omega much larger than omega naught, then what happens? AVS. So this is just to, you can refresh these concepts because they are necessary. You can see that this would be omega naught divided by omega, right? That is all. So if I, it's correct, right? Yeah, okay. And if I write in dB, this would be, if I write minus 20 log 10 omega by omega, right? Because omega by omega naught and minus, yeah, okay, that's correct. So this would be the gain. Now in this we see, if I'm taking omega in terms of decades, right? Because that is easier, because now we see there is a log function. So if omega is, let's say, 10 omega naught, or omega is, for example, 20 omega naught, right? In the two cases, what would be this gain? So let's say if it is 10 omega naught, then we know this is minus 20, right? Log 10. And if it is 20 omega naught, then what is the gain? If I, or let's take 100, I think that is better, because then we can understand it better. If I do 100, then it would be 100 to 10 power 2 minus 40, right? So what we see, if we were to look at this response, that what is happening, if omega is changing by a factor of 10, how much is your gain changing? Gain is changing by minus 20, or decreasing by minus 20, right? And that is what effectively what we draw this system, if we draw as whatever is happening, and this slope which we define, because we clearly saw that if it is happening, that means we can say the slope of this decrement is minus 20 dB per decade. So this is the term we use. Decade means it's the frequency is changing by a decade, right? 10 times. So that is the slope which we get from this simple function. Okay. And I think that I'm sure that you have seen this in basic courses, this kind of um, uh, transfer function. If you have not, do let us know, because then we can refer some basic material where you can look at this. But I think, I hope that you follow this very small how do you say, discussion of this plot, which we call it frequency response, right? This is what we have. Yeah. So now this minus 20 per decade, so that means this is, if one needs to further understand it, um, we can say that these, so one, if I define a very generic function, it's any generic uh, uh, function, which is typically called transfer function, right? So that means whatever input is being transferred to the output, how you're modeling that with, so obviously as a function of frequency, right? That is the function. So let's say if I'm writing any AS, this could be some term A naught into, it could have multiple, um, so this is what I will go into, that you can define this as, and this is directly coming from the network, right? Whatever kind of thing we are building. So let's say WP1, 1 plus as WP2, 1 plus as WP3, right? So this is generic. And what we see is in this particular, that these top, where that you have a 1 plus s term in the numerator, we can get the frequencies of the zeros from there, because as we see that when omega is equal to 0 here, so that means there is a 0 which has occurred. Now this is coming from the numerator, right? And we will go into more term understanding of the physical understanding of these things later. As of now, just we are defining these so that if you come across these terms, zeros and poles, you are not completely um, uh, oblivious to those terms. And so that is important. And I think you have probably seen this in your basic electronic courses also, these guys have transfer functions. So these are zeros, right? And the bottom ones, where we call it poles, right? And it is very clear if we see the RC circuit transfer function also, it looked like this for RC, omega p, and omega p was 1 by RC, right? This was the thing. And so this is basically this thing. How many poles and zeros does it have, this RC circuit? Obviously, there's only one pole, right? So one pole. Where is this pole? At 1 by RC. Okay. And where is this 1 by RC? We clearly saw this was this point, right? Where this was turning minus 3 dB. So if you plot this again, obviously it's 20 log, which we are plotting, because we are plotting dB versus the frequency. You see, from 0 dB we started, and then at omega equal to omega p, the gain dipped by minus 3 dB, right? That's what happened in the gain. And then it went around with the minus 20 dB per day. So this is the pole frequency, and pole frequency, or typically it is also known as, if we see the gain is decreasing, minus dB frequency, minus 3, sorry, dB frequency, right? Which is also this one by SSM, right? Because the gain is decreased by minus 3 dB. So this is the basic concepts of, you see that how the poles and zeros, and I think I can give you another circuit which you can try on your own. Right, so you can just try this to plot the same frequency response for this kind of circuit where there's C and there's R and there's V. Okay, and you can look at what frequency or pole or zero it would have. Now, one of the thing which is also defined from here, can be defined, is when once we see that the gain starts decreasing at this point, one of the important point we can say that, okay, the bandwidth of this particular circuit is this much. Because what is happening, bandwidth means that under that condition you are getting constant gain. So there is no change in the response, right? And that is what you would have expected if you didn't know that there is a capacitor there in a circuit. Because there is no speed limitation. That means whatever gain you designed it for, you are getting that. But because there is a capacitor in the hidden capacitor in the circuit, you see that because of that you start to see a decrease, and this appears at omega equal to omega p, which is where we say, okay, this is the bandwidth of our system, because after this bandwidth we see that the response of the system is changing, right? So one could also understand this bandwidth how we say in communication, right? So in communication also, where we plot, let's say, power or amplitude, again in dB or dBm there, and with frequency, and we see, so this is just a representative example so that you understand this bandwidth. So that your response may look like this, right? So let's say any internet provider or whatever you are getting at your home, it may look like this. That means you, under some bandwidth or some frequency range, right, which is typically this minus 3 dB, as we said, this term is what is your bandwidth. Under this bandwidth only, or this frequency is omega 1 and omega 2, you'll say that you're getting a particular fixed gain from the amplifier or whatever kind of circuit it is, right? There is a particular response of the circuit. So that is very important, because this bandwidth, as you saw in the time domain, this RC was referring to t time constant. And that is why you see the bandwidth and time or speed, they are equivalent to each other, right? So when we say uh, that there is high speed, that means you have high bandwidth. And high bandwidth means that you are able to get the same gain for those frequencies in the circuit. Okay. Now coming back to our example, which we were looking at. So this is just a very um, brief discussion on the frequency response, right, of a RC circuit. But now if I come back to my MOS, which is what I'm going to use, the question is, do we have capacitances here also? Because only then I would be having a limitation in the speed. Otherwise, there is no limitation in the speed, right? That is, I think, understandable. So then, where is this? If there are capacitances, where would these capacitances come from in a MOSFET, right? So for example, if I have the structure of a MOSFET, now let's look at the structure, because these resistances, it's all comes from the characteristics, right? That is where one can characterize these things, like how much is this and how much is that. So this is your standard MOS, which we have seen, right? This is your gate. And you saw that we were bringing the charge and then we were transporting the charge using BDS. That was the basic operation, which we see in this MOSFET. Now we are asking, and then we saw this, we solved the IVs and everything. And then from there, we saw, okay, that there is this VCCS formation in saturation region, which can help us evaluate these amplifiers. Now we are asking a question, okay, is if are there capacitances also hidden in my structure, which I could not see. So then let's look at node by node, because we are having nodes in our circuit. So the question is there a capacitance between gate and source? Because I do know that there is a capacitance between my, so let's call it body so that we are not confused. Because there is a capacitance between my gate and channel, because I'm having a channel here. And this is all coming because of a capacitance section, right? This is what we discussed in the starting. So that means there is a capacitance at the very core of your MOSFET structure, right? Now this capacitance divides into, because the source and drain is also affecting this formation of channel. It means this charge which we are having here is going to be divided between source and drain, right? Because it is coming because of the contribution of the source and drain. So to reiterate that again, what I'm saying is that there is a gate is bringing this charge, and this charge has two shares. One is coming from this source is claiming one its share, and drain is going to claim its share. So that means we can see these two capacitances, or this C, we can see between CGS, which is what we call as the gate to source capacitance. So whenever somebody is wondering that, okay, in a physical structure, do I have a capacitance or not? One way to very clearly see from the definition of this capacitance itself, where we see that if there is a capacitance between two nodes, Cij, the definition is that is there a change in the charge at the node J with respect to the voltage at the, because you know Q equal to CV, right? So this is the very basic way of identifying that there is a capacitance somewhere. Because if you are applying or changing the voltage at node I, and as a response to that, if there is a change in the charge at node J, that means there is a capacitance, right? And that is what happens here, that when I change G here, as a response to that, there is a charge change which in the channel happening. And charge is not the channel itself, it is basically, if we divide, because the channel, what is the node at the channel? There is no node at the channel, right? So it is basically divided among the partition or the charge between the source, because source is going to claim that charge, okay, this is my charge. Drain is going to claim its charge, that it is my charge, right? And if it is like this, the charge is like this, very uniform, then we can say half of this is source and half of this is drain, right? But if this profile is not uniform, then we cannot say the same. And I think more about this you would probably study in the VLSI design also about these capacitances, and we'll come back to it whenever you have a doubt there. Okay. But as of now, what is important for us just to know is that there is a this gate is going to change some charge at the source for the source and some for the drain, right? And because of that, there's a CGS and both CGD are going to appear in your from your device, right? And there's one more which is obviously source to body, because this you will study more in physics of transistor also, where is the origin. But this is directly coming from your PN diode, because PN diode also in reverse bias, there's a change in the charge which happens with the node voltages, which results in a CSB, and there is a capacitance here also, which comes because of the change in the charge at the PN junction depletion region with respect to CDB, right? So these capacitances, which are parasitic capacitances, obviously they are not mean, but they are also going to come in your circuit, right? So for now, we are going to take these two main capacitances and going to work with them to revise our, how would our network change now? So there's a capacitance which came between it and source. This was not existing before, right? So let's call it all small so that you understand these are small signal network capacitances, right? So as of now, we are going to take two, but you could take, let's say, you would see some of the capacitances taking CDS and basically drain to source also because of this PN junctions, as we said that there is a depletion charge which changes because of the drain to source capacitance. So you could think of this as also as a capacitance here, CDS, which we are ignoring as of now, because if we are assuming a saturation and it's mostly gate dominated channel which you are having, then the CDS is typically very small. Okay. So that capacitance we are not considering, because we see that these are the main capacitances one would see in this particular. So now once you have this revised network, one could again try to, now this is just a simple calculation, right? You could try to see that what is your gain. So this would, now we are interested in obviously frequency dependent gain. This would turn to 1 by SCGS, right? And we are also going to introduce a resistance here, because we saw last time also that the gate itself also can have a resistance, right? So let's call it RG, right? Because gate is also made of metal and it could have a resistance like how we are having in the channel. Similarly, source and drain also could have, but this is how we are going to start with first. So if we are taking a common source kind of configuration, that means obviously source is grounded. You're taking your output here, and this is an open circuit output. One can attach a load and do the calculation, but because we are just going to do without or with an infinite load like current source load, right? So for that, you see that what is the relation you would, so one can solve this circuit and try to find out AVS, which is V out S divided by V. So this is your homework, okay? You solve this circuit, and this is kind of, from this how to solve this, right? So rather than VGS, now this would be something, we call it, let's say, V in. Yeah, so this we are calling VGS, and this is, yeah, okay, this is okay. So this is just the input node, and okay, and you can calculate the capacitance and the transfer function, and then you form it in this form. That there's some A naught times, let's say, 1 upon L, right? So that you can look at poles and zeros in your circuit if you form. Okay, and once you have this, you should be able to see or plot the frequency response of your common source amplifier with infinite load, obviously, here in this case. And you can look at, okay, how that, right? You can see that how that is changing. So let's say, for example, I must just assuming that omega p1, which you are having here, is much smaller than omega p2. So this is called something called as dominant pole, right? Because it's coming first, obviously. So then your gain is constant till the omega p1 comes. And after that, as soon as omega p1 comes, see your gain starts to decrease by a factor of whatever, minus 20 dB per decade, obviously, because it's just encountered one pole, right? And then you arrive at omega p2 also is lesser than omega z1. So then you see that at this point where you have omega p2, you will have another change in the slope, because again now encountered another pole transfer function, and that slope would be now changed to minus 40 dB, because there are two poles which you encountered. One you encountered here, which gave you minus 20 dB. The pole will give you minus 40 dB, right? And then you will have at some point in the future, you will also have zero, because we are assuming that the zero is quite far off, and then you will see that it would change to 20. right? So this kind of thing you would see typically from such a trans function. Once you solve, you will see, and now it is your job to figure out that where is what is dominant pole and what is not. And this can be done when you look at these values. So I'll give you some hint about the values. GM you already know, right? GM you are going to get. R naught also you know, it is typically, this is also high, this is also high. So GM R naught and effectively intrinsic gain is higher than, much higher than 1, right? This you know. CGS typically is much higher, right? So this is also the case. The CGS is much higher than your CG. What else do you need? Yeah, RG is small. So RG is much smaller than R naught, right? I think, yeah, that is all you need to make these calls, that which one is dominant and which one is. Okay, so do solve this network, because then only you will be able to understand, and for yourself, you would be able to look at the poles and zeros of these common source stage which we have looked at. So if we were to make a circuit out of this, what we are doing is there's a RG, which is obviously coming from the gate, and till now we were just ignoring it because there was zero current, very small current here. Now we do have a capacitance coming in into the picture between source and drain, sorry, source and gate, right? And this is just from the structure which we see, and there's also a capacitance which you see from CGD, which is coming from, and here is what we are taking. This is the kind of network one. If browser circuit, it looks like this. Okay, and this is the, so this is the frequency response of. Similarly, one can calculate the frequency response of any circuit once they can make this kind of small signal. Now, where is the bandwidth? So if we were originally concerned with the bandwidth, right? We said, okay, what is the speed of these circuits? That was we were. So now from this, we can see that this would account for the bandwidth, or 3 dB bandwidth, because this gain would be 3 minus 3 dB here. So this is the bandwidth of your, particularly this common source amplifier, because after that you see that your gain starts to decrease, and then it's further decrease after it encounters the second pole. Okay, so this is all about the notion of speed as of now, right? And once we practice few examples of this, so you see that the circuit theory and the solving these equations is at the center of this when we do these things. But there's a, intuitively one can also understand that if we talk about the charging and discharging, that VI is, because there is a capacitance here, VI has to charge this capacitance, CGS, right? It's not directly that when I apply a VI, it is given as a VGS and then there is a change in the current, because that would have been the perfect situation, and which is what we were assuming, because we didn't know that this CGS and CGD existed. So when there is no CGS existing, then that means the VI is directly going there, and it is going inside, and it gives rise to the VGS, and it gives rise to VGS, and because of that there is a GM VGS, which is obviously the current which is flowing from the output, right? But now the situation has changed, because when I give VI, this capacitance, the gate to source capacitance, will take some time to charge, right? And that is giving you the bandwidth limitation, that it is temporal, in temporal terms, it is going to give you the delay in your circuit, right? And because of that, and the another thing is CGD, because this is also, that means the VI is not only transferred to VGS, it is also going to probably couple with the output, right? The CGD. Okay, so that means there is some coupling with the output, which is also going to result in some of the bandwidth limitation in my circuit. And this is directly coming from the capacitances which are coming from the MOSFET, right? So that is all about it. And I think if you do this problem, try to solve, you will get more confidence in getting these poles and zeros and plotting this frequency response.